Okay? Again, we're just doing review, but we need these concepts. Yes, Dave?
How come for the example you gave us, that high frequency gain is much higher than DC?
Doesn't matter. This is just a made-up example, but it doesn't. But theoretically speaking, it doesn't matter.
Okay.
Yeah. So I can build a transfer. I can really build a transfer function like this. That's
So in reality, is it going to be higher?
Well, in reality, for most 99.99% of the systems you deal with, the high frequency gain is zero, really. Okay. Or you're making otherwise, if it's not zero, then you're making an assumption about something. You're neglecting the time scale of something. So one of the examples that I like to give from advanced flight control course that I used to teach before is that to give a transfer function between the elevator deflection and the acceleration of the airplane. And this transfer function has the order of the numerator is equal to the order of the denominator, which means that you give an elevator deflection, you immediately get an acceleration for the airplane. Okay? Which realistically is not the case, but this is because you're neglecting the unsteady aerodynamics. You're considering the unsteady aerodynamics as a gain, right? So you give an elevator, you immediately get a force. So you immediately get an acceleration for the airplane. This is a very famous example, the transfer function of AZ, the lateral acceleration of an airplane divided by elevator. But if you account for unsteady aerodynamics like what we're doing in this course, you will have strictly proper transfer function. Strictly proper transfer function means that the degree of the denominator is strictly larger than the degree of the numerator. Okay? High frequency gain is zero. Yes, Joseph?
In the example you're talking about with elevator to normal acceleration, does that model the inertia of the airplane?
Yep.
So it's still, that's interesting.
Mm-hmm. Yeah, it's interesting. So, any question about the DC gain or the high frequency gain, please, and how this relates to the degree of the denominator and numerator. And remember, the difference in the degree shows up clearly in the high frequency limit of the phase. Okay? So if you look at Booty diagram, this guy is the Booty diagram. If I look at the Booty diagram which we generate in the lab, and you look here at the high frequency limit, if this is 360 degrees, I immediately infer that the difference in degrees between the numerator and denominator is 4. Okay? Any question about that? Any question, please? Okay, I think we covered all. Yeah.
Sorry, so I was wondering how, in that example you gave, how did you exactly determine the DC gain?
Yeah, the DC gain is very simple. Put P equals 0.
P equals
So it's 2
0.
over 1.
Okay.
Here is the definition of the DC gain. We put it here. The DC gain is the limit as P goes to 0 of G of P, right?
Oh.
Yeah.
So what is P exactly?
P is the Laplace, is S your S. Did you take a course on controls? Dynamical systems and
yeah,
control?
it's kind of different.
No. So you're always given G of S, right?
Oh,
No, do you remember? Yeah, I mean, this is the language. You're always, when they say here is a system, they give you G of S, the transfer function. It's just we have S, we call it something else here. So we call it P instead of S. That's the same thing, okay?
Okay.
So it's like in your old language, put S equals 0 in your transfer function. Wagner 1925 reserved S for something else in unsteady aerodynamics, so we cannot override. So. Okay, so we really need these concepts now to understand our unsteady flow dynamics. So having said that, having this review, our conclusion from Tudorson was what? Was that the total lift as a function of time is simply the added mass, normal acceleration at the half chord point, plus the circulatory lift, which is the quasi-steady times C of A, right? So these are the two components, the two contributions, the non-circulatory contribution and the circulatory contribution. If you look at the non-circulatory contribution, it has a little bit of a problem, okay? Why? Because it says, so ignore the one on the right hand side, and you can devise experiments or simulation that does that. A dry run for a wind tunnel, for example, like Joseph is doing. So if you look at this guy, what does it say? It says that if your input is the motion of the airfoil and your output is the lift, it says that my motion at this time dictates the lift at this time. So the relation is algebraic, has no dynamics, right? So of course this is an assumption. I mean, it's not an assumption. It's a finding from the potential flow, but the potential flow itself is an assumption, right? This is and this has a deep meaning. Remember, the potential flow is not plus square phi equals 0, right? How do you solve this guy in a steady flow? How do you solve it in a steady flow? Well, solve it whatever you like, using CFD, subject to that the V normal is prescribed, right? This is how we solve it. Okay, how you solve it in an unsteady flow where my V normal is now a function of T and prescribed? How we solve it? Well, it's the exact same equation and the exact same boundary condition. The only temporal part comes here, which means I solve the exact same equation using the exact same way, subject to the instantaneous boundary condition, subject to the velocity, the normal velocity at this time instant. I immediately get the velocity field for this time instant. Then I march forward. I just move to the next time step. I use the Vn at the next time step. I immediately get the phi at this time step, which has nothing to do from the previous phi. Okay, and didn't take any time to build up. It builds up instantaneously. So the potential flow basically ignores the time, the lag, the dynamics that the flow takes to build up the velocity field. You assume instantaneous build up for the velocity field. So this is why we have this kind of instantaneous response. When Amir did the high fidelity simulations, we observed some lag, of course, if you do viscous simulation. But this is the essence behind. Okay, the potential flow has a little bit of flaw in this respect, particularly when it comes to lag. It always gives you less lag than it should be. Okay, so this is one point. That's okay about the non-circulatory contributions. Any problem with this, please? If you have a question, come up with it. Any question? Because these physical things are, first of all, they are not very matured in books. So you're very welcome to come up with questions to enrich the discussion. So, any question? Yes, Joseph?
So is this saying the Bode plot has the gain always equal to 1 and the phase is always 0?
That's very good, yeah. We never plot the Bode plot here because, the Bode plot is intended for a dynamical system. This is not a dynamical system, it's just an algebraic relation. So you're right, it will be just constant for all frequency. But if you want to have a little bit of a meaningful thing and plot the Bode plot from the output to the input, where the input is not the acceleration but the displacement, then you will have a quadratic relation, right? Because it's quadratic in frequency, the acceleration is omega squared displacement. So anyway, there is no dynamics here, so we will focus on this part. This is the main dynamical part. And also, this is the lift that we know. This is not a typical lift. This is more of a resistance than a lift, like we discussed before. So this is our main dynamics. Main lift dynamics is here. And the transfer function is clearly there. So this is the input, and this is your frequency response. Okay? This is my frequency response. So I will call the aero transfer function. So let's see. So you have the airfoil motion. This is the added mass. So this is the non-circulatory lift. And this is Tudorson. So I will call it this. It's a transfer function. So in the transfer function language, it's a function of P, right? So remember, this is a frequency response. It's not exactly the transfer function. It's the frequency response after you substitute P for I omega or I k, because k is our frequency. Okay? So originally in the transfer function, give it another name, maybe d of p. You can call it c of p, but just to prevent confusion. This is our arrow transfer function in the Laplace domain, the transfer function that we'll use too in your dynamics and control classes. So this is now our circulatory lift. Then you add both to get your total lift, right? What we're saying is that this is a gain. This branch is just a gain. It's an algebraic relation. This is pi rho v squared added mass, and that's it. There's no dynamics. But this is indeed a transfer function. It has dynamics in it. Okay? If you have a question, please stop me.